As you can see on the screen, this will be the discussion and the answers for page 335, both the written exercises and the classroom exercises. We are in section 9.2. All right, let's do it. All right, number one. Number one is asking how many common external tangents can be drawn. Common external tangents. What's an external tangent? Well, if we were to find the center of these two circles and put a line between the centers, an external tangent does not cross that line. An external tangent does not go between the circles. That would be an internal tangent. So, how many external tangents can we get? We can find one right here. Remember what a tangent line does. It touches the circle in only a single point. And of course there's one more down here. And thus we have, in this particular case, two and only two common external tangents. In this case, well, once again, this is not an external tangent. It doesn't count. Here's an you get the idea. An external tangent and another external tangent. Why did I say oops? Close enough on this one. Because this does not touch in just one point. What does this line become? That's actually a secant, not a tangent. So I did a poor job on that. Oh, that's not much better. Ooh, that was pretty good. So we see again we have two common external tangents. For part C of number one, again, we still have, oh, that's awful. We still have one, and we have, once again, two common external tangents and only two common external tangents. For part D, ooh, do we still have any? Yes, we do. There's one right there, and there's one right there. We have two common external tangents once again. How about E? Oh, now this one's interesting. Are there any common external tangents? Well, yes. We have a tangent that does not cross the segment connecting the two centers. And it sits right here. We have one and only one common external tangent. We have broken the pattern. And what about this one? There's no way you can draw any tangent lines at all to these two circles. So we have zero common external tangents. Now we go back and we repeat the whole thing for our common internal tangents. All right, for number two, part A. Internal tangents have to go between the circles. Internal tangents have to cross that line connecting the two midpoints. So how many internal tangents do we have here? We've got one and we have two. Pretend that's straight. Two common internal tangents. What if the circles are touching? Can we draw any common tangents that cross that segment connecting the centers? And yes, we can. There is one and only one common internal tangent. Oh, I damaged the circle when I erased earlier. Okay. In this case, how many common internal tangents? Well, we can find external tangents, two of them, but there are no internal tangents. You can't draw a tangent line between the two circles. There is no between for these two circles. So zero there. Well, likewise, zero there. And of course, also zero here. Yes, there's a common tangent, but it's classified as an external tangent. It does not cross that segment. There are no common tangent lines that cross this dotted line between the centers of the circles. there are no common internal tangents. One common external, but no internals. And here, also, we have no common internal tangents. In fact, we have no common tangents at all. And we move on to number 3 first, relating to these. Question for number 3 is, which pair of circles do we call externally tangent? Tangent on their outsides. Which pair is externally tangent? No, those aren't tangent at all. These are internally tangent. And no, and no, and there it is. Externally tangent circles have one common internal tangent line. Don't let that terminology mess with your mind. Externally tangent circles, circles that are tangent on their outsides, are called externally tangent circles because they have one common internal tangent line. And how about part B of number 3, which says which pair are internally? You know, there's a grammatical error there I've never noticed. A pair is singular, one pair. It should be which pair is internally tangent, not which pair are. Which pair is internally tangent? Well, internally tangent means they're tangent on the inside, and that would be these guys. Notice, please, that internally, one circle is inside the other. Internally tangent circles, tangent on the inside of the big guy, have one common external tangent line. It's kind of the reverse. Internally tangent circles have one common external tangent line. All right, we now move on to the written exercises. Oops, wrong direction. Where did they go? I couldn't have lost my written exercises, could I? They're supposed to be here. There they are. Okay. Oh my, what was that? A passing puppeteer. Amazing. Always nice to have a puppet interruption. Goodbye. Number 1. I trust some of you remember Mrs. Rohr from your past. I'm sure some of you had her as your 5th grade teacher long ago in what feels like a galaxy far away by now. Number 1. We are told in number 1 that OT is 6. We're told that JO is 10. The whole thing here is 10. That's interesting. We're looking for the measure of JT. Well, one might say, that's kind of obvious, isn't it? Well, it's only obvious if we know this is a right triangle. Who in the world told... No one told us that was a right triangle. But they didn't have to. Because the instructions say that JT is tangent to circle O. JT is tangent... No, I'm sorry. JT is tangent to circle O. And we have a theorem that says if a line or a segment is tangent to a circle at the end of its radius, or if we have a radius that meets the circle at a tangent point, then this will be a right angle. Therefore, we do have a right triangle. And if you remember your 3, 4, 5 ratio, this is 3 times 2, that's 5 times 2, this must be 4 times 2. 3, 4, 5 ratio. Or you could use Pythagorean theorem. A squared plus B squared equals C squared. By the way, on the Chapter 8 test that I just graded last night, some of you were making some serious mistakes on this kind of triangle. Some of you were doing 6 squared plus 10 squared equals C squared, in spite of the fact that in all the previous videos in Chapter 8, I begged you not to make that mistake. Yet some of you did anyway. Isn't this the hypotenuse? The longest side? The side opposite the right angle? The side that the right angle symbol is pointing to with an arrow right there? This is the hypotenuse, and the hypotenuse always has to be in the place of C. So C this time is 10. A and B, it doesn't matter which is which. We'll put the 6 there. Now we solve. 36 plus b squared equals 100. Subtract 36. B squared is 64. Take the square root. B is 8. B is 8. All right, let's move on. Okay, for number 2, if OT is 6 and JT is 10, we're looking for JO. Oh, well, that's a little bit too easy, isn't it? Well, not really, but it's a 3, 4, 5 ratio. No. If it's a 3, 4, 5 ratio, the 5 would have to be the hypotenuse. It's not. They're trying to trick us. Again, this whole problem is just checking to make sure you understand that there's a reason why this is a right triangle. There's a reason why we're allowed to use a squared plus b squared equals c squared. If we didn't know this was a right angle, we wouldn't be able to use that. But we do know it's a right angle because we've got that theorem that says that when a radius meets a tangent line, they will be perpendicular. So we're safe. It is a right triangle. So we have 6 squared plus 10 squared equals the hypotenuse, which we will just go ahead and call OJ squared. That's 36 plus 100, that's 136, is OJ squared. Therefore, what's OJ? OJ is the square root of 136, whatever that may be. Do I have the simplified version written in my book here? Yeah, that can be simplified as 2 squared root of 34. By the way, quite a few of you got your extra credit on the test because you were correctly simplifying radicals. Well done, folks. A lot of you got 6 points added to your score by simplifying radicals. Others of you decided to throw away those points and didn't even try. It's unfortunate. Remember, bonus points are points you don't get if you don't do them. Oh, I never thought of it that way. Oops. You need to start thinking of it that way. Let me clean this up more properly here. There. All right. For number 3. For number 3, we've got what? The measured angle TOJ is 60. TOJ is 60. I never have been able to find angles like that. Oh, we'll just trace out the letters TOJ. TOJ. Start at T. Go to O. Go to J. There's your angle, 60 degrees. That's all there is to it? Yeah, that's all there is to it. Ooh. Okay, so we've got the angle of 60. I know that OT is 6. OT is, I need to get back to my yellow pen we'll use. OT is 6. And JO is, oh, that's what we're looking for. Oh, well, how easy can you get? Why do I say it's easy? Because you're supposed to know by now that in a 30-60 triangle, to go from the short leg to the hypotenuse, you just double the short leg. 6 doubled is 12. JO is 12. Done. Done. By the way, why is that true? Reviewing chapter 8 very briefly. Because a 30-60 triangle is just half of an equilateral triangle. So of course this is half of that. Of course this is half of that. Because it's half of an equilateral triangle. Moving on. Moving on. Number 4. If JK is 9, ooh, just this little piece. If JK is 9, interesting, and KO is 8, we want to know what JT is. They didn't give us enough information. Oh, yes, they did give you enough information. There's a little bit of a trick to it. But they didn't tell us OT. Yes, they did. Because in a given circle, aren't all radii the same? So if this radius is 8, then this radius is 8. See, they did give you OT. By giving you OK, they were giving you OT because all radii of a circle are clearly congruent. So, what do we have then? We have a squared plus b squared equals c squared. We have a squared, which we don't know, plus b squared, which is 8 squared, equals c squared. That's going to be 17 squared. Oh my, what is 17 squared? I don't know. I should know, but I don't. That's 49, 4. That's going to be 7, 11. Is it 319? Why is my brain not wanting to do that quickly? Why am I having doubts about myself here? Because I'm on the spot and I'm rushing too much. And I don't do well when I'm on the spot and rushing. 17 squared. 17 squared is 289. Oh, 2. Then I got 319. Oh my. 289. That's shameful. 289. I was rushing too much and wasn't thinking. Alright, subtract 64 from both sides. We get JT squared equals 289 minus 64 is going to be 220. Oh, how nice, how convenient. Because we happen to know if JT squared is 225, we happen to know what JT is. It's going to be 25. Because, no, it's not, it's going to be 15. Having mathematical issues today. Because 15 times 15 is 225. So this is 15. And we're done with that one. That's number 4. Number 5 is a pretty cool little problem here. I consider number 5 to be somewhat of an optical illusion. Why do I call number 5 an optical illusion? Because we'll discover something about this that is hard to believe by if you step back and take a look at it, you say, no, no, but yes, yes. Let's look first at just this circle and these two tangent lines. We have that corollary that I call the ice cream cone corollary because we have ourselves something like an ice cream cone. The ice cream cone corollary says that if, oh, I didn't mean to wipe out all of that. The ice cream cone corollary says, let me clean this up here so I can see it better. There. It says that if we have two tangent lines from the same point to a circle, those two tangent lines will absolutely positively be congruent. So if this is 8.2, this has to be 8.2. Well, now let's look at this circle and these two tangent lines. Same story applies. If these two green guys are both tangent to the green circle and they both have the common endpoint out there, if this one's 8.2, the other one has to be, guess what? 8.2. And then finally, in the last circle, if we have two tangent lines with a common endpoint out here, they must be congruent. So if that one's 8.2, guess what? PD has to be 8.2. So in spite of appearances, all three of those tangent segments, tangent lines, are congruent. To me, they don't really look like it, but they are. They're all congruent. All right. That ended the assignment, didn't it? It sure did. Okay, so we are done with that. How much time has passed? Tell you what, speaking of illusions, let me just take a moment to show you one of my favorite illusions. You've seen this before, but there may be other folks watching this video who have never seen this. So let me try to back up here and find my illusion. Where is it? I know it's on here someplace. Here. I drew this myself. It's not a big deal. Very simple to draw. And someplace in a drawer here I have something to help us see what's amazing about this. And I have to make this bigger. How much bigger? I would like to make it match that pretty closely. Okay, that's a pretty good match. All right, we see there are two tables. One table appears to be approximately square, and the other one is a long, thin table. Pretty obvious, right? Right. But what boggles my mind is, if I take this piece of paper, which fits on this tabletop perfectly, because I designed it that way. And I take that paper and slide it over here. It hurts the brain, but look at that. These two tabletops are actually exactly the same size and shape. But because of the way they're drawn on the board, our brain tells us that if these were actually in 3 dimensions, our brain tells us that they are very different. It's hard for me. If I step back and look at that, it is hard for me to believe that these two parallelograms are actually congruent. To me, personally, this one looks a lot longer and skinnier than that one. Yet, again, watch. Take that tabletop, good match, would you agree? I agree. Slide it over here, and we see that it is a perfect match. They are the same size and shape. Isn't that cool? That's just, the human brain just boggles my mind. And I still can't see that. It still does not look like it's possible. Yet, it is. On that note, we end for the day. Stay tuned for the new video for section 9.3. I hope you enjoyed those several-year-old videos for sections 9.1 and 9.2, filmed in front of no audience. I tried to make it look like I had an audience, and it was really fun doing that. Mr. Beard, yes? Why don't you do the introductory music? Well, that was nice when I was only doing 2 for the entire year. But now that I've done about like 90 videos, that kind of thing would get old. So those were a little bit fancier. These are more plain. I'm so sorry. But so that you don't think it's too plain, we have our old friend, Mr. Rubber Duck, saying goodbye for now.